let's go for it here. So chapter 6, we are at the end. We look at trigonometric equations here, and we're gonna, as you can see over here, we're gonna solve a little bit more complicated equations than we did in 6.5. Okay, and then we're gonna use identities. So sum to product identities, as we looked at last time here. We use these identities in order to get an easier handle on the problem itself. And then we're going to solve equations that have inverse trig functions in them. Again, I thought this would be a little too much for the scope of the class itself, but at least you want to see it before getting into calculus. Okay, so x is the measure of an angle. Then for any angle k, there is going to be k times x multiple angles. What in the world is this saying? If, let's say this here. Let's say sine of x is equal to square root of 2 over 2, right? If you're looking at a problem like this, think back to unit circle. When is which quadrant is sine positive in?
In one.
I think you guys think here right away.
All students take calculus. 1 and 2.
1 and 2 is good. Okay, so looking at unit circle. And remember, square root of 2 over 2 makes a 45-degree angle, right? Or pi over 4 or 45. That you should sort of be. So that means if sine is positive in quadrant 1 and 2, if you go 1 revolution around the unit circle, you, in a sense, you kind of say there's 2 answers if you go 1 full revolution. We're good? Then if I just change it up a little bit here, how about if I say sine of 3x is equal to root 2 over 2? Right? What this is saying is you have just tripled the amount of answers here. Okay? So you're really saying is, since there's 2 answers, 45-degree angle, right? Quadrants 1 and 2. Now I'm going to look for 6 answers this time. We're good? We're going to do it a little bit different than the textbook itself does it here. So let's go for it, though. Go back over here. Whoa, everything's gone. Okay. Let me rewrite it again. 5 or 6. Sorry about that here. This will be an easy step here. This is called solving multiple angles, and this is the whole concept of you got yourself that extra 2 pi there, and that's the problem here. So all we do, divide by 2 over here.
Multiply by 1/2.
Multiply by 1/2. Perfect. That cancels x is equal to pi over 12. That will be one of our answers. Divide by 2 here. Multiply by 1/2. And you can see, yes, of course, there is going to be a little pattern. So yes, you can solve these a little faster once you know what the first one is, especially once you know the 5 pi over 12 is going to be an answer. At that point, you can just go ahead and add it all together here, or put patterns in. So x is equal to 13 pi over 12, and x is equal to, not even going to do the work here because I know it's going to be a 12 on the bottom. Okay, and the way the book writes it, if you want to write it this way, that's fine, but it's going to be kind of like this. Do they have to be in order? No, they don't. Do they have to have those braces in front and in the back? That is not even necessary, even though there's something called set notation. But all 4 of them we will accept. Now, by dividing by 2, what we've done is we've condensed, we've in a sense gone down from 0 to 4 pi. And what we've done is we made it 0 to 2 pi only. Does that make sense? Dividing by 2 got rid of that extra rotation. And you can kind of tell because this last one over here, notice this is 17 pi over 2. If this was 2 pi, it would be 24 pi over 2. So since 17 is less than 24, you know you're sort of in that parameter between. Here it is, 0 to 2 pi. Okay, good there? Hopefully that makes sense. All right, these are multiple angles. That's what we're dealing with here. So first one has to do with a multiplier. There's a multiplier to that angle. Next one. What happens? Yeah, great. If the multiplier is actually...
So you want to have a rotation.
So you only have half rotation at this point. Yep. Okay, those that want to go ahead of me, go for it. If you want to stick with me just for a little bit longer, that's cool too. All right, should we go for it here? So first things first is this whole concept of what are we doing as far as the domain interval is concerned. So we got ourselves a 0 less than or equal to x. Looks like that's my variable. Less than 2 pi. All right, and of course the question comes up usually is, Mr. H, how come we go from 0? We are including 0, but then we get to 2 pi, we don't include 2 pi. And so that is because this makes it one full revolution. If you start off with 0, when you get back over here, if you include the 2 pi, you're including a number that's both in both revolutions. Does that make sense? Okay, so in this case, we're going to take half of everything here. So take half of this, and half of this. So we're looking for from 0
to x over 2.
Just to pi, and it's not even including the pi. We're good? So technically we're looking for half a revolution. Okay, now let's go for it here. So technically, original problem here, tangent of x over 2 is equal to the square root of 3 over 3. Then what we do is we take tangent inverse of tangent of x over 2 is equal to tangent inverse of root 3 over 2. Oh, sorry, 3 over 3. These guys cancel, and of course, do you have to do this middle step? No, you can go directly from the top piece and go directly to this right here, understanding you're adding a inverse of tangent on both sides.
How would you know which one to use, like whether to use cosine, sine, or tangent?
Oh, cool. Question is, which one do you use? Cosine, sine, or tangent? All dependent on what you start off with. Yep.
I didn't see the tangent.
All right, this one's a little tiny bit tricky on how we do this here. So remember how we define tangent in terms of y over x? If you want to do it that way, that's fine. So we know we're going to be off the unit circle, at least for a little bit here. And then we'll see how we can get back to the unit circle. So for tangent is a little funny one. Okay, but first of all, we've got to think about here. If we're going from 0 to pi, how many answers am I going to have for tangent? 1, 2, 3, 4. What do you guys say? Since we're only going from 0 to pi. So I'm going to go with only one answer, because tangent is going to be positive from here to here, right? It's positive there. But then when you're going to go over here, tangent is going to be negative, and then remember it starts repeating itself. Right? So really what I'm doing is I'm just looking at quadrant 1. So I set up my little triangle, and then I try to figure out what is this here. That means the x coordinate is 3, and that means the y coordinate is root 3. I don't have an r value because that's not given with tangent. All right, and some of you guys can actually go back in your mind real quick here, and you can actually fill in the numbers. Maybe after this, guys are more apt to do so here. But we do have a Pythagorean theorem that will give us the r value. We're going to use it. We know what x is, you know what y is. Let's go figure out what r is. So 3 squared plus the square root of 3 squared is equal to r squared. So let's go with it. How about 9? How about 3? How about 12? All right, we are the ones using this, doing the square root. So taking the square root. How come I'm not put a plus or minus by that square root of 12?
Because it cannot be negative.
R cannot be negative. Anybody? Let's see, what is square root of 12?
2 squared 3.
Yep, it's 4 times 3. 4 gets to go on the outside, so square root of 4 is a 2. Root 3 is equal to r. Perfect. Let's go over here. Now, this one's definitely off the unit circle because r is equal to 2 root 3. Roughly 1.4 or 1.5 or something like that. Okay, how do we... So remember that unit circle that we have? We want to get everything back to the unit circle because once we do that, we can figure out which one they are just by looking at a unit circle. Okay, good there? So let's go for it here. How do you get this back to the unit circle? How do I get this so that I have this? This is what I want. I want to be on the unit circle, which means r has to equal 1. How do I get that to happen with my funny looking circle?
Put it over 2 square root of 3.
Absolutely. We're just going to do this here. We're going to divide the r by 2 root 3. And we're going to divide this by 2 root 3. And we're going to divide the y coordinate by 2 root 3. Good there? Because if we divide all of them, we have ourselves, and this comes from geometry, we have ourselves a similar triangle, right? And from geometry, we learned that all similar triangles are proportional. So if you decrease one side of a similar triangle, all the rest of them are going to go down or up by proportions. So that's from geometry. That's cool. Okay, if we do that, r is equal to 1. We got it. What's going to happen here? You got to do a little bit of work over here. The x coordinate is not so fun. Okay, so a little bit of work for the x coordinate. It's going to be 3 on top, and it's 2 root 3 on the bottom, right? So we're going to multiply by root 3, both top and bottom. We'll get ourselves a 3 root 3 over 6, which cancels out. How about a
2.
root 3 over 2? Oh, the y coordinate's better, though. You got a root 3 on top, root 3 on the bottom. Those are going to be gone. What's my y coordinate going to be? I'll go with 1/2. Anybody on a unit circle or on that page where it has a unit circle, or anybody know that what's going to give you a square root of 3 over 2, comma 1/2? All right. And I needed in terms of radian measurement, not degrees. Here's the way I think about it. Is that okay? This is my y coordinate. That means my y coordinate's here, right? That means this is the smallest side, right? That's the smallest side. This has to be the 30-degree angle, right? Because 30-degree angles are always opposite the smallest side, and 30 degrees is pi over 6. So I got it. This is pi over 6. Now, what's pi over 6 equal to?
Not 30.
Remember, all that work was just to figure out the tangent inverse of root 3 over 2, right? Or root 3 over 3. So what's it equal to?
X squared
X over 2.
Squared.
So really we have this now. X over 2 equals pi over 6. Can you guys finish it off now?
Multiply by 2.
All right, I guess over here I'm going to multiply by 2 this time. I'm going to multiply by 2 as well, and again the 2's cancel. Over here also the 6 and the 2 reduce, right? 1 and 3. Final answer. Yep, pi over 3 would give you what you need. Okay, why are we doing this? This is the extension of algebra. We got to the point of no longer can we solve linear equations. No longer can we solve polynomial, quadratic, rational equations. Remember those with fractions? Now we got radical equations underneath our belt. And now we have trigonometric equations underneath our belt. Whew. We're like a black belt solving equations now. Okay, we good? We'll go back to 3 if we have some time here. This one's going to be hopefully a little bit easier here as we think about this. Okay, so sine, cosine, and tangent. Those are the ones you guys will solve quite a bit. This cotangent one over here actually is pretty easy because it works the same way as we just did with tangent. And even easier since it's equal to 1. All right, the way you work this out is probably closer to practice problem number 1. So think about what you did for practice problem number 1 because it's a multiplier to your angle. Oh, good, even better. Now we're in degrees instead of radians. So we go from 0 less than or equal to theta less than 360, but now we're wanting to do 3 theta, so 3 times 0, 0. 3 times theta is 3 theta, and 3 times 360. 1080 is perfect. Okay, you can either do it like this if you like, or you could think to yourself, you're just going to do 3 rotations or revolutions. Not sure which one's the correct word here. So we're going 3 times around the unit circle. Okay, but think about this here. I could display every single one of those, right? Or I could just add 360 to make the next revolution. And maybe adding 360 might be even faster. Good? So let's go for it here. Going back to this, cotangent. Thinking back all the times that cotangent, ooh, this is even easier because it's cotangent of 1. Let me write the equation first. Cotangent of 3 theta is equal to 1. Can I just say this? What I'm really looking for is this. 3 theta is equal to cotangent inverse of 1. Is that right?
Yeah.
Oh, this is so easy. Hold on. Tangent and cotangent are reciprocals of the x and y coordinate, right? So we're looking for when are these coordinates going to be exactly the same?
And the pi square, wait, no, pi square. Square root of 2 over 2, then square root of 2 over 2.
All right, they are exactly the same here when the x coordinate is root 2 over 2 and the y coordinate is root 2 over 2. Anybody know the degree answer? Bless you. It's a 45-degree angle. Okay, so now let's think about this here. Let's just start with this one here. So I know that 3 theta is equal to 45 degrees. But remember, I have 3 revolutions to deal with as well. Is that right? So now let's go with what in the world is 45 degrees plus 360. $405, I totally agree. Next. Ooh, 2 revolutions, 720. What's 45 degrees plus 720? I heard 765. I'll go with it. Cool. Okay, is that all we need? 3 revolutions?
Mm-hmm.
At least for the 45 degree angle. Because some people are looking at me and saying, Mr. H, no, you're missing something, you're missing something. You got it. Is there ever a time that cotangent is again also positive 1? From 0 to 360.
Quadrant 3.
In quadrant 3, right? Because tangent and cotangent work exactly the same. They're positive in quadrant 1. They're negative in quadrant 2. They're positive again in quadrant 3, and then negative in quadrant 4. So yes, we have another one over here. Anybody know the degree angle that makes this happen? Good. Yep, I heard someone say. Remember, this little part right here is going to be 45 degrees still, right? The reference angle. Then you have this extra 180 over here. So 3 theta is equal to 225. I agree. Okay, then give me, I'm not going to write it down here. As far as the operation is concerned, give me 225 plus 360. 585. Awesome. And then let's see, 225 plus 720. 945. Perfect. Okay. And think about what we're going to do here. We haven't solved it yet, right? I have one little extra step to do somewhere. I'm running out of space here.
Radian. No.
Don't convert it to radians because
Wait, no. No.
Something about dividing by 3 though. That's all.
Oh.
Right? Because you have 3 theta is equal to 45 degrees, but then what is theta equal to? All right, I'm running out of space here, so I need to go to the next slide here. So let me list them here. 3 theta is equal to 45 degrees. 3 theta is equal to 405. 3 theta is equal to 765. 3 theta is equal to 225. 3 theta is equal to 195. And 3 theta is equal to 945. Okay. So I think I'm good to go here. Is that right? Divide by 3, and I got an answer of theta is equal to 15.
Yes.
Okay, help me out here. Divide by 3, theta is equal to?
135.
135. Cool. Divide by 3,
255. Yes.
255. With a double check on that, okay?
Yeah.
All right. 225 divided by 3?
225. Wait.
75. Okay.
Oops. Oh, yeah. I see.
And then let's see. 195 divided by 3? Whoa, hold on. Sorry.
195 is the answer.
Is the answer. Can't give you guys the answer like that. Okay, 585, is that right?
Yeah.
And then 195 is the answer. Cool, okay. And then divide by this. Theta is equal to?
315.
Okay, so notice, if you go back to your original theta, Notice that all of these guys are between 0 and 360, as you eventually end up with them, like that. Okay, we good? And again, talk to me if it doesn't make sense here. Ooh, honesty question. Here we go. I think it's honestly, Mr. H, I did read 6.6 before coming to class today because I knew it was the last section. I knew it would be important. And if I knew a lot of the material beforehand, it'd be so much easier for me. Got one. I think I should need to bring like an award for that person that has been reading ahead here all this time. There's actually 2 people that most of the time have read ahead. I know who you guys are. Okay, we're good with that one here. So how would you list it? Of course, you listed the way that it was listed before, right? So you go 15 degrees, 135 degrees, 225 degrees, 75 degrees. You would notice in the back of your book, they are all listed in order, usually from lowest to highest. You don't need to list them in order, but all of them need to be there. Wow. Okay, number or practice problem. All right, practice problem number 5. Let's keep on going with those, and then see if we have time to return to practice problem number 3.
We're back to read this.
All right, I will tell you, practice problem number 5 is my least favorite problem. We'll find out why. So first things first, we should notice.
There's 2 of them that we have to work on. Well, but we have to... No.
Okay, let's go for it. So with this one, notice the topic here. It's solving an equation by squaring. Solving equation by squaring.
We're going to be doing 3
All right, when do we do this? When we do this when we are stuck, bless you. We have the same angle for sine and cosine. And we have this little trick that we learned on the identities. We did this also with identities. We did this something called the squaring method here. Kind of went like this. All we're going to do is we're going to square both sides of an equation. Oh no, we did this when we were solving square root functions. Remember, if you have a square root on both sides, you just sort of squared both sides. But this time we're not squaring because we have a square root of 3 over 2. We're squaring because we have a sine 3x and a cosine 3x. All right, so I guess I have to do a little bit of work here before I put this in here. Let me do the squaring here. So sine of 3x plus cosine of 3x. I'm going to square this, okay? So we're going to go here to here. That'll make sine square root of 3x. Good there. I'm going to go here to here, which will make, looks like, let's see, sine of 3x times a cosine of 3x. I'm going to go to the middle term, and tell me if you want me to slow down here, because there's lots of writing here. Please tell me to slow down. So, Mr. H, slow down a little bit, please. Be no problem. This one's going to be, even though it's cosine times sine, I like to write the sine first. Sine, cosine, and lastly, got myself, looks like plus cosine squared of 3x.
Should be 2 sine 3x cosine 3x. Well, yeah.
Yep, and all that is equal to 3 over 2, right? First of all. And then we get to notice a little something here. First of all, putting like terms together, and I'm also going to move the squares to themselves here. Whoa, 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 what are we doing? 3, right? 3. Sine squared of 3x plus cosine squared of 3x plus 2 sine 3x cosine 3x. Good there? All that is equal to 3/2. So don't get lost in the process. And then raise your hand if you say, man, Mr. H, I wish I would have read ahead. Not yet. Okay, I'll get to the point. All right, and then we should notice one little extra little something right here. What is that equal
to? It's a Pythagorean theorem. Wait, no.
Absolutely.
But it has 3 though.
Is it the same angles on both sides?
Yes.
Yes,
It's
okay.
1.
Yep, the Pythagorean theorem says this. If you are squaring any angle theta, right, or any sine of angle theta, right? The only thing that's required is that these two angles match. Could be 4x, could be 17x, could be 25x, could be x divided by 2. As long as the angles match, you're good to go. If the angles don't match, you're not good to go. Mm-hmm. Okay, so all that input's just going to give us a little big old 1, right? Mm-hmm. Then there's another little trick here. Anybody can tell me real quick here about something about 2 sine 3x cosine 3x? That's when it's good to have all these identities just sort of written out all in order. Just okay, I'll give you a little hint. Double angle. I'll just say that. How about that? Double angle. You can also turn to the last flap of the textbook.
Sine of 2x. Sine of 2x. We're going at that. Never mind. It's really wrong. Yeah, sine 2x.
All right, give me the formula here. What does the formula say?
Sine of 2x equals 2 sine of x cosine of x.
All right, anybody remember this formula? I know it's been a long weekend here. This is called the double angle formula for sine, right? So yeah, these formulas you probably should have in front of you. Probably should list them out. That's why I give you a sheet of paper to write all this stuff in. Anybody, what page is that?
596.
596 would be the page number you want to turn to. But notice what's happening here. Notice these terms are just x's, right? Notice whenever you write the sign of it, it's always double of your
theta
angle.
Oh, yes.
And I'll go with that. Sine of 6x is what we want. Good there. It's the 2 times the 3x. Okay. Can you guys solve the rest of it? Then you go ahead of me to solve the rest of it. And if you can't, that's okay. Just want to see you guys try. Solve this for sine of 6x. I suggest you don't draw out 12 unit circles here. Right? It's not going to be good when you do that here. So if you stuck, let's go through it together. If you have pretty good confidence to go through it, go for it here. All right, first things first, let's get this 1 out of here. So subtract 1 here, subtract 1. What is 3/2 subtract 1?
1/2.
1/2 is good by me. 3/2 subtract technically 2/2 makes 1/2. Okay, we're looking at 6 revolutions, is that right? Are we in degree measurement or radian measurement?
Radian.
We're in radian measurement. Okay, so just think of that, make sure you're there. So here it is. I'm not going to think about all 12 unit circles. I'm going to think about just what happens in one revolution. I'm going to make sure we get multiples of it and add to the other one, okay? So if in terms of just one revolution, when is sine going to give you a 1/2?
Pi over 6.
Hey, this one keeps on repeating itself. I don't know why, if the author just really likes pi over 6 or something or what. But we got ourselves right there. It's a pi over 6. Is there ever another time ever in one full revolution that sine is a positive 1/2?
5 pi over 6.
5 pi over 6. Did that before already. Okay. Okay, so if this is pi over 6, still, again, this is a negative square root of 3/2. Positive 1/2. Cool. If that's reference angle still a pi over 6, that means the angle itself is a 5 pi over 6. Everybody okay with that right there? Just to make sure we got that. Okay, now we got to deal with the 6 over here. Oh, man. Okay, here we go. Let's see, I'm debating here. Should we do it the book way and just sort of see how the book way does it? Or should we just still keep on going our way here?
Ours.
Ours, okay. I got x equals pi over 6.
Plus 2 pi.
Again.
Plus 2 pi.
Oh, sorry. How about 6x, right, is equal to
Oh, yeah.
pi over 6. Yeah, this time maybe it'd be better just to use it. Let's do it the book way because you'll see why. Because then it gets all weird and choppy, okay? Okay, let's do this here. We're going to say that this is the answer in one full revolution with a whole bunch of multiples of 2 pi. Is that right? You guys remember this one from the beginning of chapter 6, I think? It was 2 pi times the n over there. Remember that little n? Okay, so here's what we're going to do first. We're going to divide through by
6.
6 here. Or you could say we're going to multiply through by
1/6.
1/6. So x is equal to, let's see what we got here. Isn't this pi over 36? Is that right? Pi over 36 plus, isn't this going to be, let's see, pi over 3 times n. Is that right? And we still don't like that. Let's do this here. Let's make, because this will be so easy to list the answers here. Let's make this into, let's common denominators here. Because we're still not at the end of the answer right here. So it'd be pi over 36 plus common denominators. Is that good?
Yeah.
Right? Because then we can just easily go, okay, we're going to add another 12, we're going to add another 12, we're going to add another 12, we're going to add another 12. Okay, how many times are we going to add another 12?
6.
We're going to add it 6 times, right? So n equals 1, 2, 3, 4, 5.
And 6.
And I should have done it the other way here. And 0. We good? Because the 0 is going to be our first revolution, right? 1 means 1 full revolution, right? 2 means 2 full revolutions. So we're going to have 5 full revolutions and then the answer. Okay, same thing over here. Can you guys do this one over here? And then we'll put down the answers here. You guys do the same thing for 5 pi over 6. All right, let me start it here. Those waiting for me here. So I got 6x is equal to 5 pi over 6 plus 2 pi times n. Good there?
Yeah.
Dividing through by 6 on this end, multiplying through by 1/6 on this end. And you can kind of tell the numbers are going to work out sort of the same here. So this is 5 pi over 36 plus 1/3 n. Pi over 3n, and eventually becomes 5 pi over 6 plus 12 pi over 36. Oh, sorry. There it is. And again, n is equal to 0, 1, 2, 3, 4, and 5. Are we good there? Okay, not done yet. Tell how I don't like this problem too much. Okay, now let's go for it. Let's list all of them. And again, it's going to be a lot easier just to add 12 to each time. Cool. So we're starting with pi over 36, and we're going to add a 12 pi over 36 each time. Cool, so let's list them. So I just want to make sure everybody's good there. Anybody not ready to go on, raise your hand if you're not ready to go on. Cool, all right. So let's go for it here. So I got x is equal to, initially I have a pi over 36. I'll start listing them now.
7 plus 12 pi over 36.
Which make?
12 pi over 36. Wait.
We're going to add a 12 pi over 36 to pi over 6. And we've got ourselves a 13 pi over 6. Add another 12 pi over 36.
25 pi over 6.
5 pi over 36. Perfect. Then add another 12 pi. 37 pi over 36. Add another 12 pi over 36 makes 49 pi over 36. And add another 12 pi. Let's see what that's going to give us.
62 pi over 36.
61
Why?
pi over 36. Notice we're not going over 2 pi, right? Originally. Because it would be 72 pi over 6 would go over 2 pi. We're not there. Okay, now let's go back. Let's do the one with the 5 pi. Initial 5 pi over 6. Adding 12 pi over 36. Oh, sorry. I always keep on putting a 6 down. It should be 36.
17 pi over 36.
17 pi over 36. Next.
29 pi over 36.
29 pi over 36. $41 pi over 36, I think.
Yeah.
Cool. And how about a 53 pi over 36? And then how about a 65 pi over 36? Oof, got it. And then I'm going to put this little asterisk next to it. You might as well do it as well. And this comes from algebra. There it is. Since we squared both sides of an equation. So we squared both sides of an equation. We may, not always have to, but we may have that's kind of a funny word here, extraneous solutions. That's a cool math term here. So we have to plug each solution in and check. Oh man, That's no fun.
We have to check them all.
So that means we have to plug in a pi over 36 back into original. And let's think back to the original equation here. We're going to have to multiply that by 3, right? Take the sine of it, multiply by 3 again, take the cosine of it, and then see when you add it up, would they give you a square root of 3 over 2?
And whatever don't are not your answer.
Yep, and whatever don't, then they're not your answer. I will give you a little hint though. Many times they're going to come in a pattern, okay? So we're not going to spend the next 20 minutes checking this. Okay, but I'll tell you the pattern here. So the first one works, the second one doesn't. This one doesn't work, and this one doesn't work.
Is it because it's the sine graph?
Because when you squared an angle, technically what you've done is you've introduced angles that are also sine of 3x minus cosine of 3x. You introduced that sort of extra conjugate answers as well. All right, on the bottom, this does not work. 41 over 36 does not work, and 65 over 36 does not work. Cool. So I don't want you guys to check it yourself. You guys, I think you guys can plug in and check yourself easily. So then, can you guys list for me all the answers that do work? All right, again, does not have to be in order. Let me do it this way here. But I got pi over 6. 5 pi over 6, or sorry, pi over 36, is that right?
Yeah.
Why I keep on forgetting the 3 here? 25 pi out of 36. 29 pi over 36. Okay, 49 pi over 36. And how about 53 pi over 36? Is that right? True? Are you guys, is that the same thing you guys got? Cool. Okay. There it is. And again, it's going to be a little bit longer for you guys on the homework. This one does not appear on the homework. I don't think you guys will have ones like that bad on the homework. We have all these multiple angles and it gives you 6x, but that's at least gives you a good flavor for it. Cool. Okay. There's another one that's kind of set up like this, slight difference. So let's see if we can handle this. All right, let's see if I got this here. So this is going to be, let's see, 2 sine of, isn't it 2x plus 3x over 2? Then it's going to be cosine of 2x minus 3x over 2. Still equal to 0. Everybody good there so far? So then how about we get ourselves a 2?
5x over 2.
5x over 2. I'll go with that one here. Cosine of negative x over 2 is equal to 0. Okay, good so far? All right, what can we do with the 2 all the way out in front? Divide it out. I'll go with that. Let's divide out the 2 over here. Let's divide out the 2 over here. And at least we got ourselves sine of 5x over 2 multiplying by cosine of negative x over 2 is equal to 0. And then I'll mention something here. I'll just say, hey, cosine is an even function. Something fun about cosine being an even function. What happens to the negative with cosine? I can take the negative and this is what you should do in your mind. This graph should be in your mind here. Cosine curve, right?
Oh yeah, 0, 1.
Does it matter if I go to the negative x or the positive x? No, I'm going to get the exact same value. So what happens with cosine, you can drop the negative out of the angle. With sine, you can't do that. You have to get the negative to the outside. So cool. So even easier is sine of 5x over 2 is multiplying cosine of x over 2. Okay, then we go back to algebra, something called the zero product property. Or zero factor property, depending how you want to say it. What happens if two things are multiplying and give you 0?
They are 0. But one of them is 0.
At least one of them is equal to 0, right? So boom, got it. So how about sine of 5x over 2 is equal to 0, or cosine of x over 2 is equal to 0. All right, we're good there now? Okay, now we're going to do it the way the book does it. Because now it actually makes sense the way the book does it. We good? Here's what we'll do. What was our original interval? You guys talk to me. What's my original interval to this problem? It's from 0 to 2 pi, not including 2 pi. We're good? Okay, so let's go with it here. First of all, sine inverse. To undo the work of sine, we put sine inverse on both sides, but really all I need is this guy here, right? I'm going to get the sine inverse of 0. All right, so look back at your revolutions, or actually just one revolution, from 0 to 360 or 0 to 2 pi. When is sine going to be 0, and at what value?
Sine is 1. So 90? And no?
Sine is 1 at 90 degrees.
Oh,
Look at the y values.
Yeah, 0. Or 2 pi. Wait. Yeah.
Not including 2 pi.
No, just 0 then. Whoa.
0, right? Plus 2 pi n. We good? Then we go over here, and so it's at 0 degrees, right? Or 0 pi. 0 radians. Anywhere else? 180 degrees or pi. This one right here. So we got... Oh, sorry. Totally wrong here. Pi plus 2 pi n. We good? And then the question is, man, what in the world is n? We're going to leave that alone for now, okay? Because n is just a little bit more complicated now because of that 5 over 2. Good? Let's go to cosine. When is cosine 0? Good. This one's going to be like this, right? At 90 degrees? Oh, sorry. I should write this here. Hold on. Let me write this as we're trying to figure out when is x over 2 is equal to cosine inverse of 0. We're good. And that occurs at pi over 2 plus 2 pi n. Anywhere else? 270 or 3 pi over 2. 2 pi n. Okay. Again, this n value now gets a little more complicated now because that weird 5 over 2. How do we go 5 over 2? Okay, so let's do this here. Let's do what we did last time here, which we just solve it just for x. We good? So let's, I'm gonna have to rewrite this here. So everybody okay with me going on to the next slide? Let me grab the values here so I don't mess up with them here. So 0 can go away, is that right? Is that okay? 0 can go away? Right there. So how about 5x over 2 is equal to 2 pi n?
You multiply by 2 over 5.
Yeah, just let me list all of them here just so I have them here. So 5x over 2 is equal to pi plus 2 pi n. Then we have x over 2 is equal to pi over 2 plus 2 pi n. And x over 2 is equal to 3 pi over 2 plus 2 pi n. Again, I think we've done this before, right? Let's go for it here. Back to the beginning here, we're going to multiply both sides by 2. And then we're going to divide out by 5. How about that? Maybe easier enough here. Divide by 2. Multiply by 2, divide by 5. So for my x values, I got x is equal to, looks like 4 pi over 5n. For this one, I got myself, okay, kind of careful here as you do this. Whoa, where'd my x come from? Forget the 5 there. There we go. Okay. Okay. You guys give me that one, and then give me the other ones if you can. The other one's gonna be easy. Just multiply by 2. Okay, lots of thinking here, isn't it? More thinking than we did in algebra here. So 2/5 times pi would give us
2 pi over 5.
2 pi over 5. Multiplying here gives us 4 pi over 5n. Cool. Going over here, oh good, easier now. Let's multiply by 2 here and multiply by 2 on this end. So how about x is equal to, looks like just pi plus 4 pi n. And last one here, multiply by 2 here, multiply by 2 here. We got ourselves x is equal to 3 pi plus
4 pi n.
4 pi n. Okay. Almost done, almost done. So here it is. Here's what we can do. Again, n is the weird one, right? Because we don't know what n is because that whole fraction thing. So we're just going to say like this. We're going to say, okay, I'm going to start off my list already. And go back up here. And I'm going to just start putting in multiples for n, because n is just integers, right? And I'm going to go put in multiples of n until I get to pi over 2 or anything over, and I stop. We're good? So first things first, if n is 0, what is this all going to be? 0. Boom, got my first one. If n is 1, right? Still working with this one here. We got ourselves 5 pi over 4. If n is 2, hold on, let's think about this here. When am I going to get to something over 5? 10 pi over 5, would that be equivalent to 2 pi? So once I get to 10 pi over 5 or more, I stop. Good. So let's go for it here. So 0 gave me 0, 1 gave me 4 pi over 5, 2 is going to give me
8 pi over 5.
8 pi over 5.
And then we stop.
Yep, 3 is going to give me 12 pi over 5, and I stop there. No need to go anymore. We're good? Then we go on to the next one. If n is equal to 0 here, I got myself an answer of
0. Wait.
2 pi over 5, because we're adding it, right? This time. All right, if n is equal to 1, what do I got? I got myself a 6 pi over 5. Okay, I'll go with that. If n is equal to 2 here. Oh, I got myself, let's see, that'd be 8. 8 plus 2 is 10. That'd be 10 pi over 5, which is 2 pi, and doesn't count anymore. We good? Okay, then we go over here then. If we plug in a 0 for n,
Be 5 pi.
just be pi, right? Because this goes to 0. So just is going to be pi. If I put in a 1 into here,
And then it'll be 5
whoa,
pi.
too big, 5 pi already.
Oh.
Right. Then we drop down over here. If n is equal to 0, then this is,
It's 3 pi, which is over.
yeah, it's 3 pi already. Hey, totally over 2 pi already, right? Okay, therefore that's it. The answer is this right here. Okay, good there? Okay, and that's the way the book presents doing the stuff with n. You set it up as a general answer, and you start plugging in until you are out of your domain. What else is there? What else is there? I'd like to mention here the only time, notice that in this one, I'm not going to go back and check my answers. The only time in algebra when we checked our answers is when we squared both sides of an equation. And so practice problem number 5, the reason why we had to check it because of the algebra rules. Good? Okay, and we'll go with solving equations containing inverse tangent. Let's jump to this right here. Okay, this is going to be kind of weird. In fact, I should say this: solving an equation containing an inverse. You can say inverse function, or in this case, an inverse sine function, right? Or just forget about the tangent whatsoever, just put inverse function. Because the tangent function was for the example problem. Okay. So this is weird because now instead of just having a sine of x plus 1, now we have inverse sine, or sine inverse, depending which way you want to say it. So this is kind of weird, but let's go for it.
First, we move the pi over 4.
Perfect, yep. Solve pi over 4 plus 3 sine inverse of x plus 1. We're going to move this pi over 4 to the other side. And of course, this is going to be a little bit even easier one here.
4 pi over 4, which is just pi.
Yep, let's see. 5 pi over 4 subtract 4 pi over 4, which is 4 pi over 4, which is pi. Awesome. Next.
We multiply by sine.
Say again.
Just multiply by radius. And, divide by 3.
Divide by 3. You got it. That'll work. Divide by 3 here. Divide by 3 there. And I got myself sine inverse of x plus 1 of pi over 3. And you know what? We can actually solve this one of two ways. You can now take the sine of it. Oh, funny. Okay. Just want to check something out here. Let's see if I go like this. Then it pauses it. Oh, gotcha. That's not fun. Okay. All right, how do we do this here? Well, we're gonna take a sine of this side. Remember, a sine and sine inverse undo each other, right? And then we're gonna sort of squeeze it in here. We're gonna take sine of this guy. All right, so we got ourselves now x plus 1 is equal to sine of pi over 3. In this case, you could figure out what sine of pi over 3 is. Or we'll just subtract 1 from both sides. Okay, you're going to find it a little easier to write the value over here first. Usually. Can you do it the other way? Absolutely. What is sine of pi over 3? Anybody? Square root of 3 over 2. Taking the sine of 60 degrees, so you're way up along the y-axis. You're down. Okay, we do have to simplify this much as we can. How about common denominators? Negative 2 over 2. And we got ourselves 2 on the bottom, negative 2 plus root 3. Or square root of 3 minus 2 over 2. Whichever way you write it, totally fine by me. Both answers will work just fine. Okay, good there. Check something out over here. All right, we got 2 things here. Practice problem number 8, use solving an equation containing inverse functions. And this is a 2-part. Of course, it's a little bit more complicated. And at the same time, you use an identity. Use the fact that tangent inverse of x plus cotangent inverse of x is equal to pi over 2. That's a weird identity. You're saying if you take the inverse functions of tangent and cotangent, any angle whatsoever, and you add them together, they will always give you pi over 2. That's an interesting little identity there. Once you have that done, now the question is, can you solve that equation there in part B? And of course, there's a little trick to it. Okay, let me finish it off here as the last problem. Part A, let's go start it already here. So part A starts here. So first things first, this is the funny thing, there's a little trick to it, okay? I want you to just sort of see a trick here. And the trick is you let tangent inverse of x is equal to theta, which means you, right, tangent inverse of some kind of value is equal to some kind of angle. Okay, we good there? How should I say this here? Is this one of those identities you're gonna have to prove and know very well? No. This is sort of a tough problem. Finish off chapter 6. Okay. Okay, tangent inverse of x is equal to theta. What do we know then? What is x equal to then? Tangent is equal to tangent of theta. It has to equal to that because what we just do is we take tangent on both sides. Okie dokie, if that's the case, then we have this little trick up our sleeve. This is a identity that we learned. It was one of those practice problems when we were graphing the tangent function. We found out this little identity. Tangent of theta is equal to cotangent
Plus 1 minus 1. No.
Of pi over 2 minus theta. Now, do you need to know this? No. This was one of those like, oh wow, that's kind of cool. When we're doing the graphs for tangent and cotangent. Tangent is just the reciprocal along the x-axis plus pi over 2. And so that's one of the things we should notice there. So what we're going to do here, we're going to plug it in. So we're going to say x is equal to tangent theta here. How about we put in cotangent of pi over 2 minus theta? Right, again, we know that by graphs, the graphs that we did, we know that is true. I'm not sure if it was a practice problem. It was one of those homework questions that were like, hey, let's try this. Let's see if this is true. Okay, if that is the case, how about I do this here? Let's see. If x is equal to cotangent of pi over 2 minus theta, can I do this here? How about like this? Cotangent inverse of x is equal to pi over 2 minus theta. I'm going to take the cotangent inverse of both sides. You guys following the logic here. Kind of like doing those geometric proofs a little bit too for geometry. Okay, let's see. Where do we want to get to? We want to have pi over 2 on the right-hand side, don't we? So let's do this here. Let's add theta over here, and let's add theta over here. Now, the only issue is cotangent inverse of x plus theta is not going to go together. Those don't like terms. So let's write theta here. Cotangent inverse of x over here. Good there so far? We're almost there, because what is theta originally? What do we let theta be? Isn't theta tangent inverse of x? Voila. Sorry, I kind of wrote it small there, but is everything good there? So again, we've just proven this identity, that's all.
Oh. And it goes back to the beginning.
So by letting tangent inverse of x be some kind of angle, any kind of angle whatsoever, any kind of angle, by a little bit of work and the relationship that we have. We could also start off with the relationship. We could have started just saying, okay, this is the theorem we know, and we could have scooted everything everywhere, any which way we wanted. Okay, with that said, we've got to prove part B now. We're going to solve this equation here. Tangent inverse of x minus cotangent inverse of x will actually give us pi over 4. Or actually, what x, I think that's the more important, what x would give us, because this is not a identity. This is a one particular x is going to do it. So I want you guys to notice here real quick here. For part A, this right here, this is called an identity, which means this is true all the time. That's what this says. Any kind of x you put in, this will be true everywhere, all the time, no problem, anytime. Good? For part B, you're saying what x, what particular x, if plugged in, would make all of that equal to pi over 4. Good there? So we're solving for part B. We know part A works all the time. Okay, let's begin. So part B, as I'm kind of looking over my notes here, just make sure I got it right here. So we're trying to solve this, not trying to prove an identity, we're trying to solve it. What x will make this true? All right, well, what do? We add in a little trick to the subject here. we have to go back to our previous solution here. Tangent inverse of x plus cotangent inverse of x is equal to pi over 2, right? We said that. That's from part A. Well, if this is true, you guys talk to me here. See if you guys agree here. Then this would also be true. All right, what do you guys say? Yes or no? Maybe sometimes?
Yes.
I just move the tangent over. Subtract tangent inverse of x. Okay, remember, whenever we solve equations, trigonometric equations, the tough part is making them to be the same trigonometric equation or function, right? Remember how we had sine and cosine in 6.5? We're like, oh, let's just do this, right? We have to get them to be the same or a product of them. But our problem when we begin with is tangent and there's a cotangent. So how can we change it? We can change it just like this. So we're going to substitute cotangent as pi over 2 minus tangent inverse of x. Good there? And that's really the tough part right there. If you got through that part, you got the rest here. The rest is just a little bit of algebra. Negative pi over 2. Positive tangent inverse of x. Good there so far, maybe? Distributing the negative inside. Let's see what else can we do here. Put the two tangents together, so that gives us 2 tangent inverse of x minus pi over 2. This is equal to pi over 4. We add pi over 2 to both sides. 2 tangent inverse of x. Pi over 4 plus pi over 2. I go 3 pi over 4. All right, in that case, I still have a 2 on the outside. Divide by 1/2 or divide by 2?
Multiply by 1/2.
Oh, okay. What we got was, sorry, let me get it to that step here. 3 pi over 8, right? We have a double angle form like this, or half angle form, sorry. See if you guys see something looks like this in your textbook here. All right, anybody know what page number this is on?
601.
All right, page 601. Okay, let's finish it off here as we have a few minutes left here. So that means what I'm looking for is this. I'm looking for x is equal to tangent of 3 pi over 8. Which really is going to be, I got to decide here real quick here. I got to decide positive or negative on this thing. Three pi over 8. Isn't that actually less than pi over 2? Isn't that in quadrant 1?
Yeah.
So since we're in quadrant 1,
It is.
it's going to be positive. So plus right here if you want to, but it's going to be 1 minus cosine of 3 pi over 4. 1 plus cosine of 3 pi over 4. Because 3 pi over 4 divided by 2, right, would give us 3 pi over 8, right? or 3 pi over 2 doubled. So 3 pi over 8 doubled would give us 3 pi over 4. All right, anybody, what is cosine 3 pi over 4? Anybody have it? We're in quadrant 2. It is a 45-degree reference angle. So root 2 over 2, negative. And negative root 2 over 2. A little bit of work here just to try to simplify this out. So let's see if I can skip a few steps here. Tell me if you guys are okay with me writing it like this. Got my common denominator. On top I'm subtracting a negative, so I know that's going to be addition. And the 1 changes into 2 over 2. Everybody okay with that top value there? The top value, the bottom value is going to be subtraction. So that's easy enough. That's going to be subtraction. That's going to be 2 over 2 minus root 2 over 2, which makes 2 minus root 2 over 2. And what happens to my two denominators? You can, yeah, you can multiply by the reciprocal or just cancel. So 2 square root of 2 over 2 minus root 2. And what we say is we say that is simplified. I know there's like nested square roots in there, but actually technically that's simplified. Because if you try to undo, it gets all crazy. Okay, are we good there? All right, and you know, for the time left, I'm going to stop right now.